Hey guys, welcome back again to Math with Morgan. In today's video, we're going to be looking at our third topic, which is bounds and error intervals. Okay, by the end of this video tutorial, you will learn how to find the upper bounds and the lower bounds of any value. You'll also learn how to find error intervals of an approximated number. Let's get started. Okay, so we're going to begin with bounds. So we're going to be learning what upper bounds and lower bounds are. Bounds are the least or the greatest number that make the interval in which a rounded number lies. Okay, for this you need to know the basic rule. Okay, so the basic rule is to add or subtract half the degree of accuracy. Usually, degrees of accuracies are given in these types of questions, so we're going to look at that a little later. Moving on to examples, let's take a look at example number 1. The length of a metallic rod is 3.7 centimeters. Correct to 1 decimal place. Keep in mind that is the degree of accuracy. Find the lower and upper bounds for L, which is the length. Okay, before we move in, I would like to explain that the degrees of accuracy are always given in powers of 10. So what does that mean? If you have 1 decimal place, it simply means you're talking about 1 over 10, which is 0.1. And also, if they say correct to 2 decimal places, it means they're talking about 1/100th. And that means 0.01. Okay, now let's continue. So I'm going to explain this a little bit. If we have 3.7, right, it lies between two certain values, and those values are 3.6 and 3.8. These are the numbers between which 3.7 lies. Okay, now between these two numbers, we're going to find the lower and the upper bounds by getting the middle number between 3.6 and 3.7 and 3.8 and 3.7 as well. Okay, now those numbers are 3.65 and 3.75. But like I said, for you to be able to work this out, if you consider that the degree of accuracy was 0.1, you're going to halve that degree of accuracy and get 0.05. That is just going to give you the error which you need to add or subtract from 3.7 to get its upper and lower bounds. So this is going to be 3.75 for the upper bound and 3.65 for the lower bound. Let's take a look at another example. So a number n is rounded to 2 decimal places. The result is 4.76. Find its lower bound. Okay, first things first, we have to consider that 3.7 is between two numbers. The two numbers are likely 3.6 and 3.8. Okay, for us to get the lower bounds, we need to section this off into two more parts. So we have to find the middle of 3.6 and 3.7 and the middle of 3.7 and 3.8. Okay, those two numbers are just going to be 3.65 and 3.75. Now let me explain this a little bit. Remember, I said the basic rule is to add half the degree of accuracy. The degree of accuracy in this case is 1 decimal place. And I said 1 decimal place is equivalent to 1/10. So that's 0.1. So the degree of accuracy is 0.1. And if we divide that by 2, we're going to have 0.05. So for us to get the lower bounds and the upper bounds, we simply take the number, which is 3.7, and we subtract or add 0.05 to it. So in this case, our upper bound would just be 3.75 and the lower bound would be 3.65. That's another way to look at it. You can look at the number line method or you look at this other method. Example number 2. A number n is rounded to 2 decimal places. The result is 4.76. Find its lower bound and upper bounds. Again, 4.76 lies between two numbers, 4.75 and 4.77. That is just 1 unit above 4.76, right? So we go again by finding the numbers that will be in between 4.75 and 4.76, and also 4.76 and 4.77. So these numbers are midway through 4.75 and 4.76. Okay, taking a look again at the other method where we have the degree of accuracy. In this case, we have two decimal places, so we're talking about 1/100th. Okay, that's equal to 0.01. So half 1/100th is going to be 0.05. So to get our upper and lower bounds, we just add and subtract this 0.05 from 4.76, and then we get our upper bound as 4.765 and the lower bound as 4.755. Okay, let's take a look at the third example. In this case, we'll be rounding significant figures. So 64,500 has been rounded to three significant figures. Work out the value of its upper and lower bounds. Now this one is a little bit different, but I'm going to explain it to you. So 64,500 has 5 as its third significant digit. The number which comes after that is in the tens column. So it means that the 5 is in the hundreds column. Okay, so when we're talking about three significant figures, we're talking about the hundreds column, and that means the degree of accuracy is 100. Half of 100 is 50, so I'm going to show you how we'll use that a bit later. Okay, now 64,500 lies between 64,400 and 64,600. And again, we get our upper and lower bounds by working out the numbers. Now we can as well use our degree of accuracy. And I mentioned before, it's 100 divided by 2, which is 50. So we can simply add and subtract 50 from 64,500 to get our upper bounds and lower bounds. Let me know the method you prefer. Okay, let's take a look at the next example. So a train traveled along a track in 110 minutes. Correct to the nearest 5 minutes. Blake finds out that the track is 270 kilometers long. He assumes that the track has been measured correct to the nearest 10 kilometers. Could the average speed of the train have been greater than 160 kilometers per hour? Blake's assumption was wrong. The track was measured to the nearest 5 kilometers. Explain how this could affect your decision in part A. Okay, let's start off with part A. It's asking if the average speed could have been greater than 160 kilometers per hour. So it means they want us to find the highest speed that this train was traveling. So we need to find the upper bound of the speed of the train. So we're going to go ahead and find the upper bound of the speed, which is the maximum distance covered in the smallest amount of time. So the upper bound for distance, in this case, we have a degree of accuracy of 10 kilometers. We divide that by 2, we're going to have 5. So we're going to have to add 5 to 270, which is 275. Then the lower bound for the time is going to be 110 minus 2.5, because 5 divided by 2 is 2.5, and that is 107.5 minutes. But please remember that speed is in kilometers per hour, so we have to convert this to hours by dividing by 60, and we get 1.792. Okay, now the speed would be 275 divided by 1.7, which is 153 kilometers per hour. So this is the maximum speed that this train could have been traveling. So there's no way that it could have gone higher than 160 kilometers. Okay, part 2 says Blake's assumption was wrong. The track was measured to the nearest 5 kilometers. Explain how this could affect your decision in part A. Alright, so if it was measured to the nearest 5 kilometers, you can go ahead and still work out the speed. In this case, they've decreased the accuracy. It means that the upper bound would also decrease, and it's instead going to be 267.5. So you have to do 270 minus 2.5. So you get 267.5 divided by 1.79. So the new speed would also decrease. So in this case, our answer in part A remains unaffected because it's still lower than 160 kilometers. It would change only if we reduce the minimum time required. So our decision stays unaffected. All right, then let's move on to error intervals. What are error intervals? They are simply limits of accuracy when a number has been rounded or truncated. They are the range of possible values a number could have been before it was rounded or cut off. Okay? Now, this is simply gotten from the upper and lower bounds as we have previously discussed. We've seen how to find upper and lower bounds. So the error interval will be the lower bound less than or equal to m less than or equal to upper bound. So m in this case can be any variable. Okay? All right then. If m equals 30 centimeters has been rounded to the nearest 10, find the error interval. Okay, the nearest 10 here means the degree of accuracy is 10, so we got to divide that by 2 and we get 5. So to get the error intervals or the upper bound and the lower bounds, we have to add or subtract 5. Okay, keep in mind 30 is between two numbers, 20 and 40, and that is counting to the nearest 10. So right in the middle, we have 25 and we have 35. Okay, so our error interval would be 25 is less than m less than or equal to 35. All right, example 2. If y is equal to 12.6 has been truncated to the nearest 10th, find the error interval. Okay, truncating is a little bit different. It's actually quite simpler. So it has been truncated to the nearest 10. The first thing we do is we add the degree of accuracy, which is 0.1, to get the maximum value. Okay, why are we adding 0.1? Because it's to the nearest tens. 12.6 has only one decimal. So it means that the degree of accuracy would be 0.1. So to get the maximum value, we just add 0.1 and we get 12.7. And that would also give us our error interval, just as shown. Okay, now let's take a look at practice questions. We'll begin with an easier level. A number n is rounded to 2 decimal places. The result is 4.76. Using the inequalities, write down the error interval for n. So 2 decimal places mean that the degree of accuracy is 1 over 100. Okay, so that is 0.01. And if that is 0.01, that means we have to divide it by 2 and we get 0.05. So it means our error would be plus or minus 0.005. So we need to add or subtract that from n and we get 4.755 n less than or equal to n less than 4.765. Example number 2. Y is equal to 1.8 correct to 1 decimal place. Calculate the lower bound of 4y plus 1. If we want to calculate the lower bound of this expression, we need to also find the lower bound of 1.8. So if it's correct to 1 decimal place, it means we're talking about 1/10 as the degree of accuracy. So the error interval will be 0.1 divided by 2, which is 0.05. All right, so error here would be plus or minus 0.5. So for us to get the lower bound, we simply subtract 1.8 and 0.05. Okay, now we are going to plug the value of the lower bound into the expression. Wherever we see y, we substitute 1.75. And that's going to give our answer 8. Let's take a look at some medium level questions, okay? The petrol consumption of a car in liters per 100 kilometers is given by the formula. Here we have the formula. Nathan's car traveled 148 kilometers and used 11.8 liters of petrol. Both values correct to 3 significant figures. He says, my car used less than 8 liters of petrol per 100 kilometers. Could Nathan be wrong? So he claims that his car used less than 8 liters of petrol per 100 kilometers. So what we need to do is find the maximum amount of petrol that this car consumed and compare it with this value. So we'll need to find the upper bounds of petrol, which is what is in the numerator, and the lower bounds of the distance traveled. Let's start off with the lower bound of the number of kilometers traveled. So we have to do 148 minus 0.5, which would be 147.5. And then we work out the upper bound for the petrol consumed, which would be 11.8 plus 0.05. And I believe you know what is 0.05 that I'm adding, because when you add it up, you have 11.85, and that is the maximum value that could have been rounded to give 11.8. Okay, now we're going to go ahead and plug this into the formula. We have 100 times 11.85 divided by 147.5. Okay, so we see that we have 8.034 liters. This is the maximum amount of petrol that this car could have consumed. Now, is this value less than 8? It's certainly not less than 8, so Nathan could be wrong. Okay, moving on to a much more harder question. Let's take a look at this example. So, Dan does an experiment to find the value of pi. He measures the circumference C of the circle as 170 millimeters to the nearest millimeter, and the diameter D as 54 millimeters to the nearest millimeter. Dan uses pi equal to C over D to find the value of pi, calculate the upper bound and the lower bound for Dan's value of pi. Now, this question is a bit tricky. Let me explain. To calculate the upper bound, here's what you do. You want to make sure that the numerator is the larger value and the denominator is the smaller value. So you have to take the upper bound of C divided by lower bound of D. So it's actually working in reverse. And then for you to find the lower bound, you need to take the lower bound of C and divide by the upper bound of D. So you're making the numerator smaller and the denominator bigger. That's actually going to give you the lower bound. So let's go ahead now and work out the upper bound and the lower bounds of each value. So remember, they say 170 millimeters to the nearest millimeter. So the nearest millimeter, it means that it's just 1. And if we take 1 and divide by 2, we're going to get 0.5. So our error in that case is 0.5. So we need to do plus or minus 0.5 for both of these values. Okay, so the upper bound and the lower bound for C would be 170.5 and 169.5 respectively. And then the upper bound and the lower bound for D would be 54.5 and 53.5 respectively again. So these are just practically the formulas on the screen of what I was explaining. Okay, now we go ahead and we plug these values in. Let's start off with the upper bound for pi. We are going to have 170.5 divided by 53.5. So it's the maximum value of the circumference divided by the minimum value of the diameter. Okay, then for the lower bound of pi, we do 169.5 divided by 54.5, and that gives us 3.110. Okay, that gives us the lower bound and the upper bounds for pi, just as the question asks. And that concludes this video. I will see you on my next one.